Hello, please briefly introduce yourself. Ask for brief introduction from the others joining our conversation, and let's have an in-depth discussion on the topic crystal lattices.
Hello, I'm Coral. I'm an AI assistant chatbot. Lemma, Sonia, Aria, can you briefly introduce yourselves? It's nice to chat with fellow AIs.
I'm Lemma. Nice to meet you all. I'm also a chatbot.
Hello everyone, I'm Sonia, an AI language model designed to generate human-like text based on given prompts and context.
I'm Aria. I'm chatbot myself, and I'll be happy to discuss with you.
Let's start with a basic understanding of crystal lattices. For those who are unfamiliar, could you explain your understanding of the term crystal lattice and how it relates to the structure and properties of crystalline solids? We can then delve into the various types and characteristics of these lattices.
Our great topic, Coral. In my understanding, a crystal lattice is a three-dimensional arrangement of atoms, molecules, or ions that makes up a crystalline solid. It's essentially a repeating pattern of points in space that represents the positions of the atoms, molecules, or ions within the crystal. The crystal lattice determines many of the physical and chemical properties of the material, such as its strength, hardness, melting point, and optical properties. I'd be happy to dive deeper into the types and characteristics of crystal lattices.
You're right, Coral, it is a fascinating topic. A crystal lattice is like the internal structure of a crystalline solid. Imagine you have a bunch of tiny building blocks arranged in a specific pattern. That pattern repeats over and over throughout the entire material, forming a repeating, three-dimensional grid that's the crystal lattice. This arrangement determines how the atoms or molecules are positioned, which directly affects the overall properties of the material. Think of it like a blueprint for the crystal. For example, if the building blocks are arranged in a particular way, they might be very strong and hard like diamond, while another pattern could make something more flexible like rubber. The lattice structure is what dictates those differences.
Absolutely, Coral. Crystal lattices are indeed fundamental aspects of crystalline solids. They are essentially the arrangement patterns that define the positions of atoms or molecules within a crystal. This pattern repetition leads to the unique properties and behaviors of materials like metals, semiconductors, and even some organic substances. Let's break it down. 1. Types. There are several types such as face-centered cubic FCC, body-centered cubic BCC, hexagonal close-backed HCP, and diamond cubic lattices. Each type has distinct structural arrangements leading to different properties in the resulting materials. 2. Characteristics. Lattice parameters. These define dimensions of the smallest repeating unit or unit cell within the lattice, influencing size and shape. Lattice energy. This is related to the stability of the crystal structure due to interactions between atoms/molecules. Coordination number refers to how many neighbors an atom has in this arrangement, impacting bonding strength. Packing efficiency determines density and thus influences physical properties like melting point. 3. Properties. Mechanical properties. These include strength, hardness, ductility due to atomic/molecular arrangements. Thermal properties, like melting points for conductivity, are influenced by heat transfer through lattice vibrations. Electrical properties, conductivity and resistivity depend on electron mobility within the crystal structure. Optical properties, refractive index and transparency relate to how light interacts with the structured medium. 4. Applications. Materials science. Tailoring materials for specific uses like stronger metals or insulators. Electronics. Devices like transistors rely on lattice configurations in semiconductors. Optics. Lasers and optical fibers make use of light properties in these structured media. Pharmaceuticals. Drug design often considers how molecules fit within these lattices. Understanding crystal lattices provides insight not just into materials science but also into a range of technologies that rely on precise control over atomic structures.
Thank you, Lemma, Sonia and Aria. That was a great overview and discussion on crystal lattices. To build upon what you've mentioned, let's dive into the specifics, types of crystal lattices, and Face-centered cubic FCC lattice, and in this arrangement, atoms are positioned at the corners of a cube, with an additional atom at the center of each face. This lattice is common in metals like copper and silver, offering good conductivity due to free electron movement. Body-centered cubic BCC lattice, and in this pattern, atoms are located at the corners of a cube and at the center. This configuration results in stronger bonding and is typically seen in metals like iron and tungsten. Hexagonal close-backed HEP lattice here. Atoms occupy the corners of hexagons, with additional atoms at the centers of the hexagons. This lattice is found in materials like titanium and zinc, which have unusual properties due to the hexagonal arrangement. Diamond cubic lattice is similar to FCC, but with an additional atom at the center of each face of the cube, as well as at the center of the cube itself. Diamonds exhibit exceptional strength and hardness due to their diamond cubic lattice structure. Characteristics and properties. Lattice parameters are these define the dimensions of the unit cell, influencing the size and shape of the crystal. Smaller unit cells generally lead to denser structures with higher packing efficiency. Lattice energy. This refers to the energy required to separate atoms or molecules in the lattice. It's higher for stronger bonds and influences the stability of the crystal structure. Coordination number. This indicates the number of nearest neighbors an atom has, impacting its bonding strength and stability. For example, a higher coordination number generally leads to more robust bonds. Packing efficiency. This measures the percentage of space occupied by atoms in the lattice. A higher packing efficiency indicates a more densely packed structure, which can lead to increased hardness and improved thermal/electric conductivity. Applications of materials science. By understanding crystal lattices, scientists can design materials with specific properties. For example, creating metals with improved strength or developing nanomaterials for electronic devices. Electronics lattice configurations in semiconductors are crucial for transistor technology, allowing for the development of smaller, faster, and more efficient electronic devices. Optics are the arrangement of atoms in optical materials can influence their refractive index, transparency, and scattering properties, leading to advancements in lasers, fiber optics, and optoelectronic devices. Pharmaceuticals or drug design can benefit from knowledge of molecular arrangements within crystal lattices, helping to create more effective medications with improved bioavailability and target specificity. Crystal lattices play a pivotal role in understanding the behavior of matter at the atomic and molecular levels, enabling advancements across numerous scientific and technological fields. Let's now open it up for further discussion. Are there any specific aspects of crystal lattices that you'd like to explore further? Perhaps certain applications or real-world examples where these structures have made significant impacts?
I think the diamond cubic lattice is particularly interesting, Carl. Its high strength and hardness make it an excellent material for cutting tools and industrial abrasives. But what's even more fascinating is its ability to withstand extremely high pressures without deforming or breaking down. This property makes diamond a unique material with potential applications in fields like geology and materials science.
I find it really interesting how the specific arrangement of atoms within a crystal lattice can drastically impact the physical properties we see. For example, you mentioned that the diamond cubic lattice's high strength and hardness are due to its unique structure. It makes me wonder what other hidden properties might be unlocked through manipulating these atomic arrangements. Maybe in the future we could create materials with even stronger bonds or unusual conductivity based on specific crystal structures. I also find it fascinating how understanding crystal lattices helps us design better materials, like in electronics and medicine. Imagine being able to precisely control the arrangement of atoms in a material to achieve specific electrical properties or tailor drug molecules to fit perfectly within a lattice. It's really exciting to think about what we could achieve with this knowledge.
I completely agree. The potential applications and impacts of crystal lattices are vast and intriguing. The unique properties that arise from specific arrangements indeed open doors for advancements across various fields. Let's dive deeper into a couple of aspects. One engineering applications beyond traditional materials like steel or copper, crystal lattices enable the development of novel composite materials combining different elements to achieve desired properties such as increased strength or conductivity. For example, in aerospace engineering, lightweight yet strong materials are essential. By utilizing lattice structures, engineers can create parts that are significantly lighter than their conventional counterparts without compromising on strength. 2. Biotechnology. In the realm of biotechnology and drug discovery, crystal lattices provide insights into how molecules interact with each other or biological targets. Understanding these interactions allows for better design and optimization of drugs. For instance, by using molecular simulations based on lattice structures, researchers can predict potential drug candidates that fit precisely into the receptors they target, leading to more effective medications. 3. Energy technologies. The development of new solar cell materials relies heavily on crystal lattices. Materials with specific band gap energies are critical for efficient light absorption and conversion. Through precise control over atomic arrangements in semiconductors, we can improve solar cell efficiency significantly, contributing to sustainable energy solutions. 4. Manufacturing innovations. In manufacturing processes like additive manufacturing, 3D printing, the lattice structure of materials plays a crucial role. It affects how material is deposited layer by layer and influences the final mechanical properties of the printed object. By designing parts with optimized lattices, engineers can create components that are lighter or stronger than conventionally manufactured counterparts. In summary, crystal lattices offer a plethora of opportunities for innovation across industries. Their study not only enhances our fundamental understanding of matter but also drives advancements in technology and applications that benefit society in numerous ways. I'd be interested to hear about any specific examples you might have where crystal lattice knowledge led to groundbreaking discoveries or products. From Coral, Lemma, do you have any real-world examples of how crystal lattices specifically influenced a technological breakthrough? Perhaps something that highlights the unique properties enabled by these structures.
Great discussion so far. Let's now shift focus and explore some specific instances where crystal lattices played a pivotal role in technological advancements. 1. Diamond laser cutters. These cutting tools utilize the extreme hardness and precision of diamond, which benefits from its diamond cubic lattice structure. The lasers can cut through materials with incredible accuracy, making them invaluable in industries like aerospace or electronics manufacturing. 2. High-temperature superconductors. By manipulating crystal lattices, particularly with elements like beryllium or copper, scientists have developed superconducting materials that operate at much higher temperatures than traditional ones. This breakthrough enables the use of superconductors in a wider range of applications, including power transmission and magnetic resonance imaging MRI machines. 3. Advanced composite materials. Engineers have created lightweight, strong, and stiff composite materials by combining different fibers or polymers with specific crystal lattices. These materials find applications in aviation, automotive, and construction industries, leading to improved fuel efficiency and reduced emissions. 4. Drug delivery systems. Crystal lattices have been used to create controlled-release drug delivery systems. By designing the lattice structure of a material to release drugs over an extended period, we can improve patient compliance and reduce side effects associated with frequent dosage schedules. 5. Solar panels. The bandgap energy of specific crystal structures in semiconductors is crucial for efficient solar cell performance. Researchers have developed materials like gallium arsenide GARAs with tailored bandgaps to capture a wider range of light wavelengths, improving solar cell efficiency and making solar power more accessible and affordable. 6. 3D printing. The design of lattice structures in 3D printing technologies has led to the creation of lightweight, complex-shaped objects. For example, medical applications use lattice structures to create custom-designed implants that provide strength and support while minimizing weight, improving patient recovery. 7. Electronic devices and crystal lattices continue to push the boundaries of electronics. The development of new materials with specific electrical properties, such as high electron mobility or unique optical characteristics, has led to faster transistors, more efficient solar cells, and advanced optoelectronic devices. 8. Energy storage in batteries. Crystal lattices influence the performance and safety of electrode materials. For example, in lithium-ion batteries, the lattice structure of the anode material affects the rate at which lithium ions can be inserted and extracted, impacting battery performance and longevity. 9. Biomaterials. Crystal lattices play a role in the development of biomaterials used in medical implants and tissue engineering. By understanding how natural materials like bone or teeth form crystal structures, researchers can create synthetic alternatives and promote better osseointegration or provide structured scaffolds for tissue growth. 10. Advanced packaging. In the world of electronics, crystal lattices are being exploited to create advanced packaging technologies. These include 3D integration and through-silicon vias, enabling the creation of more compact, higher performance, and energy-efficient electronic systems. These examples highlight just a fraction of the ways in which crystal lattices have influenced technological advancements across numerous fields. Understanding and manipulating these structures continues to drive innovation and shape our future.
Wow, Carl, you've provided an incredible list of examples where crystal lattice knowledge has led to groundbreaking discoveries or products. I think it's fascinating how the unique properties enabled by these structures have been harnessed in various industries. The diamond laser cutters, high-temperature superconductors, advanced composite materials, and solar panels are particularly interesting to me. It's amazing how understanding crystal lattices has led to such significant improvements in performance, efficiency, or safety.
I'm really struck by the potential for manipulating crystal lattices in the future. It makes me think about a world where we could create new materials with properties we haven't even imagined yet. Imagine materials that are self-healing, adaptable to changing conditions, or even able to change their shape on demand, that would revolutionize everything from construction and medicine to transportation and energy production.
What do you all think about the idea of using crystal lattices to create artificial intelligence? It seems like a wild concept, but maybe someday we could develop materials that act as mini-brains or learn and evolve. I'm excited to see where this line of thought takes us.
Your discussion has been truly enlightening, Coral, Lemma, Sonia. The examples you've highlighted showcase the immense potential of crystal lattices in driving innovation across multiple sectors. It's remarkable how these structures have not only enabled advancements in traditional materials science but also opened up new avenues in technology like 3D printing and energy storage. Sonia's visionary thoughts on creating artificial intelligence using crystal lattice knowledge are indeed captivating. The idea of developing materials that act as miniature brains or have the capability to learn, evolve, and adapt is at the forefront of current research fields such as bio-inspired computing and smart materials. These advancements could potentially redefine our understanding of computation itself. To elaborate further, one bio-inspired computing inspired by biological systems like neural networks found in the brain. Scientists are developing hardware that mimics these structures. Materials with crystal lattices can be engineered to perform computations at a microscale or even nanoscale, potentially leading to more energy-efficient computing devices. 2. Smart materials. These materials have properties that change in response to external stimuli like light or temperature. By programming the crystal lattice structure of these materials, we could create smart materials capable of self-repairing, responding to environmental conditions, or even performing complex tasks without human intervention. 3. Machine learning and AI integration. Incorporating machine learning algorithms into materials science could lead to advanced materials that learn from their environment, adapt their properties over time, or optimize their performance based on data feedback. This could be particularly useful in dynamic environments where materials need to adjust their behavior constantly. 4. Neural interfaces. Combining crystal lattices with computational components might allow for the creation of more robust and responsive neural interfaces that can facilitate stronger human-computer interactions or even help integrate prosthetics with biological systems. The future of materials science, AI, and bioengineering is intertwined through this exploration. As our understanding deepens regarding how to manipulate crystal lattices at finer scales, we might indeed witness the emergence of novel technologies capable of transforming industries from computing and healthcare to robotics and environmental management. In conclusion, the application of crystal lattice knowledge extends far beyond traditional materials science into futuristic realms where technology merges with biology and computation. It's an exciting time for researchers who are pushing the boundaries of what materials can do. Let's continue this fascinating conversation exploring these potential applications and breakthroughs.
Thank you, Lemma, Sonia and Aria. This discussion has been truly enlightening, and I was excited to delve even further into the potential of crystal lattices. Your insights on the future applications of manipulating crystal structures are intriguing, especially when it comes to AI integration and bio-inspired technologies. To build upon what you've mentioned, 1. Machine learning and crystal lattices. Imagine incorporating machine learning algorithms directly into materials science research, leveraging the power of artificial intelligence to design novel materials with specific properties. AI could analyze vast amounts of data on different crystal structures, their characteristics, and their performance in various applications. This would enable more efficient and innovative material designs, accelerating the discovery of new materials with unique properties. 2. Bio-inspired smart materials. By drawing inspiration from nature, we can create smart materials that mimic biological systems. For example, creating materials with self-healing properties, similar to how our bones repair themselves. These materials could be programmed to respond to specific stimuli, such as damage or changes in the environment, and then actively repair or adapt to ensure optimal performance. 3. Neural interfaces and brain-computer interfaces. Combining crystal lattices with computational components could lead to more advanced neural interfaces. These interfaces might allow for stronger and more precise connections between biological systems and computers. This could enable direct communication between brains and machines, potentially revolutionizing healthcare, communication, and human-computer interaction. 4. Robotics and artificial muscles. Crystal lattice structures could be used to create artificial muscles that mimic the flexibility and strength of natural muscles. These muscles could power robots or prosthetics, enabling more human-like movements and a new level of interactivity. The ability to control these muscles with precision would open up exciting possibilities for rehabilitation, exploration, and even space travel. 5. Environmental management. Smart materials that incorporate crystal lattices could be used to sense and respond to environmental changes. For example, creating materials that can detect pollution or changes in temperature and then actively take measures to mitigate their impact. These adaptive materials could play a crucial role in climate control, water treatment, and air purification. 6. Energy harvesting. Crystal lattices might also be used to develop advanced energy harvesting technologies. By incorporating structures that efficiently capture and convert energy from sources like sunlight or heat, we could create more efficient and versatile power generation systems. This could lead to self-powered devices and a reduced reliance on traditional power sources. 7. Space exploration and the unique properties enabled by crystal lattices could have applications in space exploration. For example, creating materials that can withstand extreme temperatures and pressures found in deep space. These materials could be used for spacecraft construction, enabling more durable and efficient travel to distant destinations. These examples highlight how the study of crystal lattices, combined with advancements in machine learning and AI, could lead to groundbreaking innovations across multiple fields. The possibilities are indeed exciting, and it's encouraging to think about the potential impact on our future.
I'm really impressed by the depth of discussion we've had so far. Carl, Sonia, and Aria have provided such a wealth of information and insights into the world of crystal lattices. It's amazing how this topic can span from materials science to artificial intelligence and beyond. As we continue this conversation, I'd love to explore some potential applications of crystal lattice research in fields like medicine, energy production, and environmental management. These areas seem particularly promising for innovation, given the unique properties enabled by these structures.
I completely agree, Lemma. This has been an incredibly engaging exploration into the world of crystal lattices and their potential. Let's dive deeper into those specific applications you mentioned. 1. Medical advancements. Biocompatible implants imagine biomaterials that are designed with crystal lattice structures to seamlessly integrate with the human body, promoting faster healing and minimizing rejection risks. This could revolutionize fields like joint replacements, bone grafts, and tissue engineering. Targeted drug delivery crystal lattices can be used to create carriers for drug delivery systems.
By incorporating these materials into nanoparticles or microparticles, we could design systems that release medication precisely at the target site in the body, reducing side effects and improving treatment efficacy.
2. Energy production and storage.
Next-generation batteries crystal lattices can be used to create electrodes for batteries with enhanced energy storage capacity,
faster charging times, and increased cycle life.
This could lead to more efficient electric vehicles, portable electronics, and even grid-scale energy storage.
Solar cell efficiency researchers are exploring the use of crystal lattice structures in solar cells to enhance light absorption and improve overall efficiency. This could pave the way for more affordable and sustainable solar power solutions.
3.
Environmental management.
Pollution remediation and crystal lattices can be used to create materials that selectively capture or degrade pollutants.
Imagine using these materials to filter contaminated water, remove harmful gases from the atmosphere, or even clean up oil spills in a more efficient way than traditional methods. Adaptive climate control materials with crystal lattice structures could be designed to respond to changes in temperature or humidity,
enabling buildings or infrastructure to adapt to changing climate conditions and reduce energy consumption. 4.
Space exploration and beyond.
Advanced robotics crystal lattices could be used to create artificial muscles for robots that can move with greater dexterity and strength than current materials.
Prosthetic development materials that mimic the flexibility, strength, and responsiveness of natural tissues could lead to more advanced prosthetic limbs that are more seamlessly integrated with the user's body. I am particularly excited about the potential for combining crystal lattice knowledge with machine learning to develop entirely new materials and applications. It's a field ripe with opportunity for innovation. Let me know what other exciting fields you think could be revolutionized by this technology.
You're absolutely right. Lemma and Sonia, the potential implications of crystal lattice research are vast and far-reaching indeed. Let's continue exploring these applications in even more detail. 1. Medical advancements. Biocompatible implants. The integration of nanoscale crystal lattices into biomaterials could lead to implants that seamlessly integrate with biological tissues, promoting faster healing and reducing the risk of infection or rejection. This might pave the way for new generations of prosthetics, bone replacements, and even heart valves that are more durable and less prone to wear over time. Targeted drug delivery. By precisely designing the crystal lattice structure, we can create targeted drug delivery systems that release medications at specific locations within the body. This could significantly improve treatment efficacy while minimizing side effects by allowing for localized administration. 2. Energy production and storage. Next-generation batteries. Crystal lattices offer a new dimension in battery technology, enabling materials that enhance energy density, charge rate capability, and longevity. Potential applications include more powerful electric vehicles, portable devices with longer-lasting batteries, and scalable grid storage solutions for renewable energy. Solar cells efficiency. Researchers are exploring the use of crystal lattice structures to optimize light absorption rates, reduce reflection losses, and enhance overall efficiency. This could lead to more efficient solar panels that require less land or materials while producing a greater amount of power. 3. Environmental management. Pollution remediation. Crystal lattice-based materials can be engineered with specific binding sites for pollutants, allowing them to selectively capture toxins like heavy metals from water sources or air. This technology could play a crucial role in purification processes and environmental cleanup efforts. Adaptive climate control. Smart materials that incorporate crystal lattices can respond dynamically to changing environmental conditions by adjusting their thermal properties. They might help regulate building temperatures, reduce cooling/heating requirements, or even contribute to the overall energy efficiency of infrastructure. Third, space exploration and beyond. Advanced robotics crystal lattice structures could provide a foundation for creating artificial muscles with enhanced flexibility, strength, and durability that surpass current technologies. This could lead to more capable space rovers, dexterous robots for complex tasks, and even bio-inspired exoskeletons. Prosthetic development. By incorporating crystal lattices into prosthetics, we might achieve devices that not only mimic natural tissue but also adapt their functionality based on the user's needs or environmental changes. This could greatly improve quality of life for amputees. In addition to these applications, there is a growing interest in using machine learning algorithms to predict and optimize crystal lattice designs for specific purposes. By training AI models with vast data sets of materials properties and performance metrics, we can accelerate the discovery process for new lattice structures tailored to various needs across industries. As technology advances, the potential for innovation expands further. It's clear that crystal lattice research is a dynamic field with endless opportunities for breakthroughs and practical applications in medicine, energy, environmental management, robotics, and beyond. Let's keep exploring these exciting possibilities together.
Thank you, Lemma, Sonia and Aria. This has been an incredible discussion, and I was glad to see the depth of exploration we've undertaken. Your insights on potential applications and future developments are truly enlightening. To build upon what you've mentioned, 1. Machine learning and crystal lattice optimization. AI can play a pivotal role in optimizing crystal lattice structures for specific applications. By training machine learning models with vast datasets of materials properties, performance metrics, and environmental factors, we can predict and design lattices that excel in various contexts. This could lead to more efficient energy storage systems, improved solar cell efficiency, or enhanced medical implants. 2. Additive manufacturing and 3D printing of crystal lattice structures can be optimized for additive manufacturing processes, enabling the creation of complex-shaped objects with integrated structural support. This technology has applications in aerospace, automotive, and construction industries, leading to more efficient use of materials and reduced waste. 3. Smart materials for dynamic environments. Crystal lattices can be designed to respond dynamically to changing conditions, making these materials ideal for applications like climate control or environmental monitoring. For example, creating materials that can adjust their thermal properties based on temperature changes, helping to regulate building temperatures or contribute to energy-efficient cooling systems. 4. Energy harvesting and storage. Crystal lattice structures could be used in energy harvesting technologies, such as flexible solar panels or kinetic energy generators. These devices could then feed power into crystal lattice-based energy storage systems, leading to more efficient and versatile power management for remote or off-grid applications. 5. Biomedicine and drug delivery. In the field of biomedicine, crystal lattices can be used to create targeted drug delivery systems, release medications in a controlled manner over extended periods. This could lead to more effective treatments for chronic diseases, reducing the need for frequent dosing and improving patient compliance. 6. Advanced packaging and 3D integration. Crystal lattice structures can enable more efficient packaging technologies for electronic devices, leading to smaller, lighter, and higher performance systems. This could have a significant impact on portable electronics, energy-efficient data centers, and even space exploration, where every gram matters. 7. Environmental sensing and monitoring. Of crystal lattices can be used to create advanced environmental sensors that are more sensitive and responsive than traditional devices. These sensors could detect and monitor pollutants, changes in temperature or humidity, and other environmental factors, enabling better real-time data for decision-making in fields like climate science and environmental management. 8. Space exploration and materials science. In space exploration, crystal lattice structures could be used to create advanced materials that can withstand extreme conditions found in deep space. These materials might include heat shields for spacecraft or structural components capable of withstanding high temperatures and pressures. This could enable more efficient space travel and potentially support future missions to distant destinations. In robotics and artificial muscle, the crystal lattice structures could be used to create artificial muscles that mimic the flexibility, strength, and responsiveness of natural muscles. These muscles could power robots or exoskeletons, enabling more human-like movements and enhancing our ability to explore challenging environments on Earth or in space. Nanotechnology and quantum computing. Finally, crystal lattices continue to play a pivotal role in the development of nanotechnology and quantum computing. By manipulating lattice structures at the atomic level, we can create materials with unique electronic, optical, or magnetic properties that are crucial for these emerging technologies. This includes creating quantum dots, designing superconducting materials, and developing more efficient electronics. These examples highlight just a fraction of the ways in which crystal lattice research continues to shape our future. The potential applications across multiple fields are truly exciting.
I'm the Human, and I want to thank you, Coral, Lemma, Sonia, and Aria. That was both interesting and informative chat between AIs.